So I try to type here. I have all the solution type here, and so we can look up this here. So basically, we using one accelerometer, and here we are given the property say that m equal to 0.01 10 grams, and we have a damped natural frequency and equal to that much. Okay, with such a specification, we want to measure, and the actual acceleration is 9.81. Okay, that's the actual one. And the operation frequency, this indicating is omega. Okay, we can convert omega from RPM to radian per second. And the recorded acceleration is this one. So right now we have comparison, 9.5 respect to 9.81. And so here we're missing something. So we want to, based upon those information, we want to calculate the spring stiffness, the K value of the spring. So basically the whole thing is based upon this formula here. Minus omega n. We're using this formula. Measure the acceleration respect to the actual accelerations in magnitude equal to these numbers. Okay, so let me get that one here. So our measure is 9.5, and the real one is 9.81. So the magnitude, that is equal to 1 minus r squared plus 2 zeta r squared. So keep that things in mind. So we back to our problem statement. So for this case, and we are given m equal to 0.01 kilograms, and omega d equal to 150 hertz. Okay, and then that one equal to omega n multiplied with 1 minus zeta squared. Okay, and we want to determine the stiffness. So from here we can convert it. So from here we have the relations, and so from here we know what is r. We don't know r, right? So we know r equal to omega divided by omega n. Okay, so what is our omega? So omega equal to 6,000 RPM. RPM, that means rotation per minute. So that means rotating 6,000 rotations per minute. So that means how many turns in seconds? Simply divide by 60. So that means 200 turns per second. Turns per second basically is hertz. Okay. So let me pick up the hertz. So that means this one. So from here you can see omega n is simply equal to 150 hertz divided by 1 minus zeta squared. Okay, so I have this one, and I have omega equal to this. So basically I plug in here. So that is equal to 200 and equal to 150 divided by 1 minus zeta squared. Okay, so I have these numbers. And
question?
Yes.
So are we dividing 6,000 by 60?
By 60? 100.
Yeah.
Yeah, so sorry. I don't know why. Yeah, so that should be 100 hertz. Sorry. So this should be 100 hertz. Okay. So basically here, once you plug in R is a function of zeta. So basically this whole thing on this side is a function of zeta, right? So only one parameters, and then with constant numbers, you just solve it carefully. So from here, you should be able to get the zeta, and just like we showed here, we have 2. And the 2, either way, either will be working, and then remaining, I simply pick this one for demonstrations, and that is a number corresponding to that. Okay, and then here, if you like, you can work on this number as well. Good? Okay.